Okay, so I want to talk about the rationale for these significant figure rules that we need to deal with. So when we're measuring something, we're limited by the tools that we have, right? You know, our rulers only go to the millimeter. Our scales might go to the 10th of a gram, or maybe in some cases the 100th, or maybe even the 1,000th. But at some point they stop, right? We can only be precise to a certain point. So that means when we report digits, we can't report to more digits than we can really measure, right? So let's say in reality we have two paper clips. Okay. One that weighs that much, and the other one that weighs this much. Okay. Now we have some scales, right? Now this is an incredible amount of precision. You'd be hard pressed to find a scale that could get anywhere near this, probably anywhere in the world. But let's say these are the true values, right? So what we're talking about here is to the nearest gram, there's a 10th of a gram, 100th of a gram, 1,000th of a gram, 10,000th of a gram, 100,000th of a gram, millionth of a gram. So now we're into the micrograms here, and 1/10,000,000th of a gram. Okay? Or if you want 0.4 micrograms. So an incredibly small value. All right? Now, the best scale that we have at our school can measure to 0.0001 gram. And a scale like this costs like $3,000. Very expensive. If we put this paper clip on this scale, what readout would that scale have? Well, it would read out 4.937. And what would it do with this digit? It would look, I don't know if it can look, but it would judge based on this, and it would round it up, and we would get a 3. And then we would say our uncertainty is that. Does that jive with what we have here? Is this value between 4.9372 and 4.9373? Absolutely it is. It's 2.6, right? So it's right in there. So that's what this scale would read, okay? So we're certain of all these digits, but this digit is a rounded digit, so it's not exactly what the real digit is, right? It's a rounded up digit, but it's the best this particular scale can do. Now let's say we took this other paper clip, and we're not going to haul out the big expensive scale. We're just going to use our, 10th of a gram scale. Well, we put our other paper clip on there, and we get 4.9, because we looked at this digit. It's a 3, and rounding rules say that we just round to that. Now here's the question. We're being scientists, and we don't want to lie to anyone. Oh, and sorry, we also have to do this. We don't want to lie to anyone. What is the value of the mass of both of these paper clips together? Okay, so I want to add these two values together. So I can't really know, we're saying these digits are this, but based on our measuring tool, we can't know beyond a certain point what they really are. So when I add these two things together, we'll just skip that uncertainty for a second, and we go 4.9373 grams, and to that we add 4.90, well actually nothing, not zeros, we don't even know what they are. We add them together, you type that in your calculator, what do you get? What your calculator is going to tell you is going to tell you 9.8373 grams. Is this correct? Why? I don't know what these are. I have no idea what they are. And yet I'm reporting as if I do know what they are. Okay? So when we have a scenario like this, we have a rule that says I can only show in my result to a number of digits after the decimal equal to the one with the least amount. So this one has the least amount after the decimal. I'm only allowed to show to here. This is the last digits that's considered to be significant, because we don't know what these are. And in fact, if you took these values, both the four, and added them together, you would not get this number. You would get different values than this. Okay? So the only significant numbers that we can say for certain are good are these. So to report that, we look one digit past, it's at 3, and we arrive with rounding that this is 9.8. This is considered to have two significant digits. Two significant digits. By the way, this had 1, 2, 3, 4, 5 significant digits, and this one had 2 significant digits. Okay? So all I want to do is get the rationale across to you. When I'm adding values, if one is more precise than the other, the least precise value dictates what we can say about what we know at the end of the day. Okay?